Okay, this is section 2.2, using second derivatives to classify max and min values and sketch graphs. So in order for us to actually go through this, we're going to have to talk about what a second derivative actually does for us. What does it give us? So our objectives are to classify relative extrema of a function using the second derivative test and to graph a continuous function in a manner that shows concavity. So there's a word that we haven't seen yet, and it's part of our vocabulary. Concave up and concave down goes with concavity. Second derivative test, and point of inflection. This is probably going to take us 2 videos, so I'm going to try to keep both of them under a certain time, like maybe under 20 minutes. We'll see. But there's probably going to be 2 videos because there's a lot when it comes to actually sketching these graphs. Okay, let's get started. Let's talk about concavity first. The concavity of a graph describes the way the curve is facing. That's more of just a way for you to look at how to see the graph, because that's not an official mathematic definition. We will get to that. If the graph is concave up on an interval, then the curve faces up. Basically looks like it's opening up or curving upwards. And then, so a lot of people say like the mouth of a smiley face. You see the smiley face right there, right here. The mouth looks like it is curving up right there. If the graph is concave down on the interval, the the curve faces downwards like the mouth of a sad face. That one right there, doing that. So let's look at the couple of examples here. And it's important to see that there's 2 examples in each one. Letter A seems to be the most obvious one. It looks like that whole graph just kind of curves upward. You can kind of see that one in graph A. That's usually not too much of a problem. In graph B, while the graph itself is decreasing, it's going down, the curvature is still up. Okay, so if you were to start taking like tangent lines, and this is the actual official definition, which is probably listed below me. I'm getting ahead of myself, but if you were to take tangent lines, every tangent line that you draw would be here, 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 here. And then on B, it would be here, here, here. What you can see is that all of the tangent lines here are beneath the curve. Okay, if all of your tangent lines are beneath the curve, then it is concave up. Vice versa, if all of your tangent lines happen to be above the curve, it's concave down. Again, in C, you can clearly see that that thing looks like it is curving downward. Okay, it definitely looks like there's a curvature here which is going down. And all the tangent lines that you can draw are going to be above the curve. Likewise on D, it's harder to see because it doesn't actually seem like it's coming back down, but the curvature of it is still facing in a downward general direction. So all the tangent lines that I can draw are above the curve, meaning the curve is actually facing downward. All right, so you can read the it says in graph A and graph A, in graph B and graph C and D. It's pretty much what I just said. So the definition is if f is concave up on an interval, then f prime is increasing. And that's because all of the slopes are going in an increasing fashion. For example, in part A, the slopes from here to here are all negative. And then they hit 0 when they get here, and then they start going to positive. So negative numbers to 0 to positive is constantly increasing. Here, all the slopes are negative, but they're starting to get less and less negative as they start to approach a 0 slope. They'll never get to it, but that's the idea. And then vice versa, I'm not going to draw this one, but f is concave down if f prime is decreasing on that interval. So in the previous section, we found that f was called increasing and f prime was positive. If f was decreasing, then f prime was negative. So the same exact idea is going to work here for concavity. If f double prime is positive or greater than 0, it's number 1 here, then the graph is concave up. If f double prime is less than 0, then the graph is concave down. Okay, and the general idea behind that is the second derivative is a derivative of a first derivative. So really it's asking you, how are my slopes changing? Okay, once again, are they going in a positive direction, increasing? Are they going in a negative direction, decreasing? So that's why the positive gives you concave up, the negative gives you concave down. Okay, a couple of important reminders, and then we'll actually start getting to a couple of examples. F of x is your actual y value, height of your graph. F prime of x shows us the slopes of the tangent lines, which will show us increasing and decreasing. And F double prime is your concavity now, which shows you whether the graph basically is curving up, concave up, or curving down, concave down. Okay, let's go ahead and look at what we're going to actually do with this. We're going to do what's called the second derivative test. I'm actually going to try and sketch some stuff in this little box here so you can see what we're talking about. So the shape of concave up is basically that little U, and then the shape concave down is almost the upside down U. The graph suggests that we might be able to use these to find relative max and mins, and we can. So the idea is this. If we know that we have a critical value, so let's just say, for example, we've already done the first derivative, and we know that we have a critical value at a specific number. Well, at that number, if we can determine the concavity, we can determine whether it's a max or min. Let me explain what I mean. If, for example, and this will go with number 1, if, for example, I say that we have a critical value at some point, and at that point, we can say that the graph is concave up. So let me draw my dot a little bit bigger there. So that was our critical value. The graph is now concave up. I'm just going to erase that. That just looks horrible. I apologize. There's our critical value. The graph that goes through that is concave up. Well, since I know that we have a critical value and the graph is concave up, it shows us that clearly this has to be a minimum. It's at the bottom of the concavity being up. Same exact idea. If we have a critical value and the graph is concave down through that critical value, well, then that indicates that we have to have a maximum on the graph because it has to be at the top of the hill. So that's how we can use the second derivative test. One thing you should notice right here is that if your second derivative equals 0, because it's the only thing we didn't talk about, then that's actually going to be an inconclusive result, and you have to go back to the first derivative test to find maxes and mins. Okay, so where it says be careful, it's just about how you actually think about this. Just, again, you'll see what we do here, but try and draw yourself a little symbol. I think it helps to see what's actually happening. Okay, so first of all, in example 1, let's find any extrema and the graph and graph the function that's given. So to find extrema, using specifically the second derivative test, we're going to have to take the first derivative first. This will tell us increasing and decreasing. So the first derivative is going to be 3x squared plus 6x minus 9. Okay, that's your first derivative. I do want to find the critical value, so we'll set that equal to 0. This cannot be undefined because it's a polynomial. Don't have to worry about the undefined part. Let's factor out or divide a 3 out of there. So we get x squared plus 2x minus 3 equals 0. And then we can factor this. Looks like it's going to be x plus 3, x minus 1. Therefore, my critical values are going to occur when x is negative 3 and when x is 1. Those are our critical values. Now, here's where the second derivative test is really nice and convenient. If I take the second derivative, now this is going to tell me concavity. Take the second derivative, we're taking the derivative of the first derivative, so that's 6x plus 6. Yeah, I can find the intervals of concavity if I want to, and probably should eventually. But if all I want to do is find the relative extrema here, all I have to do is I have to take the critical values that we found in the step above and plug them into my second derivative. So I'm going to test out f double prime at -3. Well, if I plug in -3, we get -18 plus 6, which is -12. -12 is a value which is less than 0, meaning that the second derivative is negative or concave down. So that is concave down, which indicates, since it was a critical value and it's concave down, it's going to look something like this, which means that we have to have a maximum at -3. Same idea for x equals 1. Let's check that one out. If I plug in 1, we get 6 times 1, which is 6, plus 6 more is positive 12. Positive 12 is greater than 0. Since the second derivative is positive there, that indicates concave up, which means that you have some kind of an upwards looking opening, which means since it's upwards and there's a critical value, then you have to have a minimum at the bottom of that hill. So I know I have a minimum at f of 1. So now we actually do need to find these values because we're going to need those to sketch the graph. So let's go ahead and find f of -3 because this is going to give us our y value, and f of 1. Okay, so we're going to have to plug some stuff into the calculator here, or if you can do the mental math, that's even better. So f of -3 is going to equal 14 when you plug that into the original function. F of 1, let's see, 1 plus 3 is 4, minus 9 is -5, minus 13, -18. So now we have our max. This is our max, local maximum, and this is our local minimum. So we have the points. Let's go ahead and see if we can't sketch this thing. Okay, and our scale was actually done very well for us here on this graph. So I've got a maximum at -314. So -3 comma 14 is going to be, let's see, 10, 12, 14, 16, right about here or so. And then let's see, the minimum value was at 1, -18. So at 1, -18 is going to be right about here, or fairly close to it. And again, this is a sketch. We're trying to do a decent sketch, but it doesn't have to be perfect. Okay, let's see. What else do we know? Okay, we didn't actually go through the process, but we may as well. So from the first derivative test, we can figure out increasing and decreasing. So if I put -3 and 1 on here, we did this in the last section. I'm going to take a value which is less than -3, like -4. I'm going to plug it into both of these here. -4 plus 3 is negative. -4 minus 1 is also negative. So a negative times a negative is a positive, which means increasing. And then between -3 and 1 is 0. If I plug 0 into both parentheses, I get a positive times a negative, which is negative. So decreasing, which makes sense because I have a maximum at x is -3, so that makes perfect sense. And then it should go back to increasing because I have a minimum at 1, but you can plug a number anything greater than 1 in there, and you're going to get a positive times a positive. So there we go. So it looks like that this is going to be increasing to decreasing to increasing. Would probably be a good idea if we could find some more information, but since that's all we're really asked to graph right here, we're going to add additional information in there as well. Something we haven't talked about yet will be a point of inflection, which is coming later in here, but that's something that I'm not really going to include on here. So let's see. So we're going to go from increasing to decreasing to increasing. Not too bad. It would really be good if we could have found all the x-intercepts. Excuse me, that would have come from the original graph. You'd have to do a bit of factoring to figure out where those are. But that's a good enough sketch for what we were trying to do right there. And you can see concave up and concave down on your graph. Okay, let's go ahead and look at the next example. Find any relative extrema and graph the function given by 3x to the fifth minus 20x cubed. So let's go ahead and find the first derivative, which is going to be 15x to the fourth minus 60x squared. Let's find our critical values. So we're going to set that equal to 0. That does not look like a squared. It's better. All right, we can factor a 15x squared out, which is just going to leave x squared minus 4. Okay, so we're going to get 15x squared, x minus 2, x plus 2 equals 0. So we're going to get that x either equals 0 or plus or minus 2. Those are our critical values. So we've got 3 critical values to test. I'm actually going to go horizontally here to give myself a little bit more space. Let's do the second derivative. Second derivative is going to be 60x cubed minus 120x. And what I need to do is I need to plug in all of my critical values now to see if they are maxes or mins. So we're going to do f double prime of 0. Well, plugging 0 into both of those just gives me 0. Okay, that's actually inconclusive. Inconclusive. Does not tell me whether we have a max or min. So we can actually figure out whether 0 has a max or min by going back to the first derivative test, which we will do eventually. Let's plug in -2. All right, so if I plug -2 in, we get -240. Okay, that's definitely less than 0, which means it's concave down at that critical value, which means it looks like a frowny face, which means that we have a maximum when x is -2. Let's try the last one. If x is +2, and we plug that one in, we are going to get, I believe that's just the opposite actually, it's +240, which is greater than 0, which means concave up. So it looks like a smiley face, and that means we have a minimum. Okay, so we're going to need to find our values of the function at those places. So let's do the actual function at 0. Once again, that's just 0. That's the easy one. Let's do the function at -2 and the function at +2 and see what we come up with. If we plug in -2, if I did that correctly, we get 64. If we plug in +2, we get -64. Okay, so the last thing that we need to do is we're going to go ahead and find our intervals of increasing and decreasing. So I'm going to go back over here and do the number line. And you might ask yourself, well, if I was just going to do the number line anyway, why did I go ahead and do all the second derivative stuff? It probably would have been easier just to use the number line here, but the second derivative test is more convenient for some slightly more complicated functions. Okay, so if I plug in something less than -2, like -3, and again, I'm plugging it into these right here. Anything I plug into 15x squared, because I'm squaring the value, that's going to be positive on the outside. So if I plug in -3 into the first parentheses, that's negative. If I plug -3 into the second parentheses there, that's also negative. So I've got a positive times a negative times a negative, which is still going to be a positive. So increasing on that interval. Okay, so anything in between -2 and -2 and 0, like -1. Again, anything on the outside is positive. If I plug -1 into the first parentheses, it's negative. If I plug -1 into the second parentheses, it's positive. So I've got 2 positives times a negative, which means decreasing. If I plug a +1 in, So I'm going to get a positive times a negative times a positive. Well, that's actually, again, negative. This explains why at 0 we did not have a max or a min. And then if I plug something in greater than 2, like 3, everything is positive, so it's increasing there. Okay, so what we've got is, I've got 3 points. I've got 0, 0. Okay, that's where we had a critical value that did not change direction. I've got -2, positive 64, which looks like it's going to be, I don't know, right about here or so. That's close. And then I've got +2, -64, which again looks like it's going to be right about there or so. That's our minimum. And then what it looks like is the graph is going to go from increasing all the way up to here, come down here. It is going to be a critical value, which means it's got to level out for a second, but then it's got to go back to decreasing again till it gets to here, and then it's going to increase once it hits the minimum and go this direction. And there you have it. All right, that's where we're going to finish video 1. We will come back and do the rest of this in video 2.